Hello and welcome to this Contact Engineered Solutions webinar. This is Tools for Treatment, the science behind treatment strategies for new National Pollution Discharge Elimination System, or NPDES Rules Compliance in Tennessee. This training is primarily intended for site development engineers, site owners, municipal stormwater program team members, and maintenance providers within the state. Our goal in bringing this information to you is to provide you with a baseline for understanding the new regulatory requirements. And as you view today's material, you are encouraged to stop the recording as necessary to capture critical information contained on the slides that can later help you with your site compliance needs. We really do hope you enjoy today's training. Today's training is brought to you by Chris Allen and Jacob Dorman. We are both regulatory managers for Contact and share responsibility within Tennessee. For those unfamiliar with Contact, Contact is a full-service site solutions provider. We offer more than just solutions for your stormwater quantity and quality needs. We have a full array of pipe and structure options as well, and we would encourage you to look at our website for more information on how we can help you with your site development projects. So I'm Jacob Dorman, and I'm going to kick things off today. We're going to first discuss key elements of the new permit. We're then going to review pollutant removal processes associated with common stormwater control measures. And then I'm going to wrap up my portion of today's training by looking at the new SCM treatment train guidance within the permit. Chris is then going to take over and complete today's talk by providing critical information necessary to properly design proprietary practices under the new permit. So to understand where we are going, we need to better appreciate where we have been. So very briefly, let's discuss the rulemaking process that has given us these new NPDES rules. It has been an ongoing process for nearly a decade. And within the last couple of years, the 2021 and 2022 calendar years, progress to get to a final rule really ramped up. And this final rule is based on Clean Water Act requirements, a negotiated settlement between affected stakeholders that were involved in a lawsuit, and public input from other stakeholders, such as the MS4 community or the manufacturing community. And what these rules really do is they do a great job of establishing post-construction pollution reduction design requirements, specifically as that relates to performance of our post-construction stormwater control measures, as well as seeking to improve the operation, inspection, and maintenance of those practices. There's also included in the rule some discussions of riparian buffers that we are not going to address. We are going to keep our content to stormwater control measures today. Overall, the new rules and permit are intended to provide permittees with compliance flexibility. They're not intended to be unnecessarily prescriptive. And I think as we go through today, you can see some of the flexibility in how permittees are going to be able to interpret certain stormwater control measures and where they might fit within the toolbox. And a critical piece here is also this permit implementation timeline. The new permit was effective in September of last year. Phase 1 communities are going to be responsible for implementing their own rules consistent with the statewide rules as those permits are reissued. For Phase 2 communities, you're going to have a 2-year window from October to fully implement the new rules. And so as we start to get into what is in the permit rules, it's always helpful to understand what the agency's expectations are. And we have some assistance readily available in that the Tennessee Department of the Environment and Conservation released their draft permit rationale with the draft permit in 2021 that provided some clarifying language related to stormwater control measures and how they can be classified, because how an SCM is classified is critical moving forward. And so instead of leaving things up for individual permittee interpretation, we can go directly to the permit rationale and establish where TDEC's expectations are. And so for this presentation and for designs moving forward, the key to keep in mind as it relates to the various SCMs available is that the vast majority of them can be classified by the treatment process on which they rely. And that's why over the next couple of slides, we are going to take some time to dive a little deeper into how various categories of SCMs are intended to function, better understand those processes so that we ultimately know how they can be classified moving forward. And so that brings us to the water quality treatment volume table. This is a critical new piece of information that is included in the new NPDES rules. And not only does it establish the types of treatment, okay, it also clarifies that there is a new statewide design storm, and that's going to be the 1-year, 24-hour design storm. The design storm is variable across the state and is going to be dependent upon individual rainfall characteristics of each site. When Chris presents here in just a little bit, he's going to go into great detail on how we go about using that information. But I wanted to point out as part of this slide that we have now an established storm, and it's the 1-year, 24-hour design storm. And that is going to be the storm we utilize to generate the amount of water quality volume that's required to be treated. So how are we supposed to interpret this table? I like to think of this as a menu. And as a dad of 3, we occasionally go out to dinner, and it never fails that not a single one of the children wants the same thing. And that's really how we need to think about this treatment table. It's a menu. And when our site allows us to do one thing, we can pick whichever treatment type works for us. When we run into site constraints, we simply have to choose from a different part of the menu. But all of these treatment types are to be considered entrees. And so what do I mean by that? When I say treatment type, I'm really talking about this category here on the left of the chart. It highlights various processes associated with different types of stormwater control measures. There's also this column in the middle that talks about the water quality treatment volume, or WQTV. That is the amount of runoff that's required to be treated by the specific treatment type selected for your site. The more efficient your SCM is at reducing pollutants, the less volume you are required to treat. On the flip side of that, lower category SCMs that are less efficient at pollutant removal must treat more volume to increase the overall load reduction. And so how do you know what type of treatment or SCM fits into each of these categories? So this table also includes some really important notes that are not all inclusive by any means, but provide examples, in this case, of what types of systems fit into this specific category. And so I think the way that this table is laid out, when you think about it as a menu of options, it really helps determine how to go about designing a site. Again, the takeaway here is that if your site has constraints that wouldn't, say, allow you to use column or category 1, not even category 1, just the first category there, infiltration, evaporation, transpiration, then you simply choose a different category to pick an SCM from. You're going to have to deal with slightly different volumes, but it's not as if you don't have options when you run into certain site constraints. I think it's a really critical part of this table that we need to keep in mind. So now that we've talked about some critical aspects of the permit, I think it's important we talk about how we go about removing or reducing pollutants. And so let's now talk about the processes associated with the treatment volume table. So in this category, this category 1, infiltration, evaporation, transpiration, and reuse. That's what we're going to be talking about now. So this is a category that really mirrors sort of a natural water cycle. And what do I mean by that? The processes deployed in this category very much mimic what happens in nature. So there's infiltration again. So how are we getting runoff back into the ground? There's evaporation and transpiration, or ET. So this is transforming that liquid runoff into a different state. Meaning, how are we getting through, say, the use of vegetation, runoff back into the atmosphere? This is water reuse. So we're reclaiming the use for something else beneficial. And then another sort of good rule of thumb for this category is this is really sort of a capture category, more along the lines of, say, a hydraulic or a hydrologic process, in that there would be, using SCMs in this category, there would be no discharge of runoff from your site when you're treating that first 1 inch of runoff. This makes practices that fully infiltrate a preferred first line of defense against polluted runoff. 100% of pollutants in runoff fully infiltrated are retained on site. This is the most effective way of eliminating runoff and addresses both water quality and water quantity concerns. So we wanted to take a second to also kind of highlight what the sort of dominant process within each of the categories is. And so here we have infiltration. Within that first 1 inch category, infiltration is going to be the thing or the process that influences the runoff volume the most. And so what are the various influences on infiltration? So the amount of rain or the amount of precipitation that has fallen is an influencing factor. Whether or not the underlying soils have been compacted and have capacity to infiltrate the runoff we're putting through the SCM is a component that influences infiltration. The slope, so how fast runoff moves across a surface intended for infiltration, is a contributing factor, as well as land cover. Generally, it's particularly influential here if the site was, if this is, say, a redevelopment site, and if the land cover was previously something that maybe was impervious, and we're trying to maybe put an infiltration practice there, that prior impervious nature of the underlying soils is going to impact the ability of an infiltration-focused practice to function. At the end of the day, infiltration is primarily intended to maximize runoff and pollutant reductions. And where it's feasible, it makes a lot of sense. So what are some key considerations when we think about applying infiltration practices on our site? So the underlying soils must be capable of accepting the entirety of the volume that we're sending to that system. So we need to test for infiltration capacity under fully saturated conditions, and we want to avoid infiltration where underlying conditions of the soil affect its ability to accept infiltration. We want to remove large sediment and trash prior to it entering an infiltration system. So we want to really pre-treat these systems. This is not only going to improve the longevity, but it's going to protect that filter media that treats the runoff before it infiltrates, because that media can occlude and will occlude, and we want to extend its life cycle as best we can. There are many studies out there that show how vegetation, again, that ET aspect, helps with not just media infiltration rates, right? But also by breaking down and creating habitat along the root systems for microorganisms to live. What those end up doing is creating cavities inside of that media that help improve the infiltration rate. We also want to be thinking, maybe not as the most critical feature of all this, but we want to think about the ability of these systems, specifically infiltration-based systems, to handle future storm intensities and return frequencies. And there's a great deal of new information out there that we're not going to talk about as part of this presentation, but that we would encourage you all to go and look at, that really talks about how the southern United States is impacted under future climate conditions and what that may do to some of the SCMs we're selecting today as we look into the future. So what types of systems or SCMs are we going to see in this category? This category is going to include bioretention without an underdrain, because we want to fully recharge that design volume. So this is essentially a 100% water quality volume. We are also going to see rainwater harvesting and reuse in this category. And we need to recognize that while, again, this may not be practical everywhere, we are not discouraging the use of infiltration type systems. We simply believe that these systems are appropriate where the underlying soil conditions support their use. And again, if you run into a design situation where you cannot infiltrate, you are not penalized under the new permit. You simply select something from one of the other categories. So let's move forward with looking at another category. This category is going to be biologically active filtration with an underdrain. It's a very specific category when you think about how the rest of them look. This category, you are required to treat the runoff generated from the first 1.25 inches of the design storm. Again, all of these are equal from a menu perspective. Again, these are all entrees, and so this would be just simply, instead of steak, this is chicken. So what does this category discuss? So what is the first 1.25 inch treatment category primary process? So in this instance, we're going to be looking at a filtering process that mixes some chemical and biological functions in there. We're talking a little bit more about that here in just a second. But in all practical purposes, this means this is going to be bioretention that doesn't fully infiltrate. So in this instance, this is where these are going to be bioretentions that have underdrains. A critical element of the permit rule with this category is that water quality treatment volume table includes the words must provide 12 inches of internal water storage. If you don't know what internal water storage is, there's a picture of it here on the right. And the next slide, we're going to go into a little more detail of it. So the dominant process within this category is, again, biologically active filtration. So we're not necessarily infiltrating the entirety of the design storm here. And the primary mechanism for flow out of this system becomes this essentially L-shape underdrain. And so what are the things that influence the effectiveness of this biologically active filter? And so the engineered media composition becomes critical. We need to do a good job of QA, QCing this media because how well runoff flows through this, how quickly it gets to that internal water storage zone is helpful. The other piece of this is the depth of that internal water storage zone. So what are we talking about here? We're talking about this lower portion. This is critical because as you notice from the circle in the diagram here, this is an upturned elbow on a typical underdrain. The control feature of this underdrain is the invert out of that upturned elbow. So everything below that upturned elbow is going to remain wet, and it's going to create sort of this anoxic zone and allow for denitrification. Another critical element within this category is the need for a vegetation or a soil component, right? We've got to make sure that we have bio in the biologically active filtration. So there's a couple of key pieces from a process standpoint that we wanted you all to keep in mind. So again, the primary considerations for this are going to be your media infiltration rate. We need to understand that that's relatively low for non-proprietary systems. And this is going to be one where we start to see some proprietary systems like things like some of the biofilters that contact manufacturers being allowed because of their primary pollutant removal processes being allowed in this category. And so their flow rates are going to be much higher. The benefit here of, say, a proprietary system within this category is there's a fair amount of QA, QC in excess of what you typically see for non-proprietary systems. And that helps ensure that when those systems get installed, that media flow rate operates at what the expectation is. There's also going to be, again, a presentation of vegetation or soil. There's that E, T, and I benefit associated with that, as well as, like I described with the last category, you create preferential flow paths and microorganism habitat along the root zones of the vegetation. And that is really critical to ensuring media operates as expected. There are distinct wet and dry zones within this category. The upper portion has to dry out between storms to be able to accept the next storm, which means we have to ensure that we have adequate depth of that filtering media because the wet elevation is set at the top of the invert for the upturned elbow, and everything below that is going to remain wet. So again, what is an example of some types of systems that we may expect to find within this category? So again, we're going to have bioretentions with underdrain, like you see in a sidewalk planter there on the left, as well as several proprietary biofilters that are depicted in the center and on the right. We also wanted to include a picture of an upturned elbow in the event you weren't familiar with it so that you could see how it's oriented and how it sort of differs from a traditional straight pipe out underdrain that you find in some current bioretention designs. So let's move on to the third category. Again, this is one where there are multiple processes being deployed within this category. And this is kind of the first change we see in the water quality treatment volume, in that this category is the first 2.5 inches of the design storm or the first 75% of the design storm, whichever ends up being less. And as Chris is going to demonstrate, that becomes pretty critical when we start thinking about the types of practices we deploy within this category. But there are a number of examples in the notes section that should be referenced to understand what type of systems get included here. So what is the treatment type category being deployed? So there's actually two dominant processes deployed within this category. First, we have a sand or a gravel filtration. So a process in which solids are reduced by a medium, generally a media, blend or a membrane. And we also see that ponds end up in this category. I like to think of this category as that that drawer in our kitchen that just kind of collects stuff. We see it in the picture here. And, in my house, it's got extra iPhone chargers and tape and a flashlight for when the power goes out. And yes, the chalks and the dry erase markers. It's got everything you could possibly need, Band-Aids in there. And that's really sort of this category. It's kind of a catch-all for some of the remaining practices. So let's talk about the two dominant processes. So the first we want to talk about is this idea of filtration. And there's two distinct types of filtration that need to be discussed. The first is what we see here on the left, which is the surface membrane filtration, right? So this is where we're going to physically kind of strain sediment out of a system. A coffee filter is a great example. On the right is depth or bed filtration, and that's where the filtering happens inside the media matrix. So there are space, sort of interstitial space in there that sediment gets collected. And both of these can have high surface area, and that really kind of allows you to have some flexibility in your designs. So what are we talking about really when we're talking these two types? Okay, so what are some more, I guess, detailed understanding of these? So inside of this sort of physical straining or filtration, we're going to have the sand filters and the perlite medias. We're also going to have membrane filtration. Again, we're providing an inert physical barrier to collect solids. From a functionality standpoint, sedimentation plays a big role in the filtering effectiveness. And what do we mean by that? So the filter surface is going to have the sediment hit up against it, and that sediment then drops down to the bottom of the filter. And what we end up seeing here, because it's sedimentation is playing a role, and this is an inert filter, we get really good results and control of solids and the pollutants that end up being attached to those. So things like metals and total phosphorus or phosphorus. What we don't get out of these systems, because it's inert, is there's no reactive media component. And so we don't see a lot of dissolved or soluble pollutant removal in these. And like anything else, but specifically related to filters, longevity needs to be considered. So we know all SCMs are going to need maintenance. All filters eventually occlude. And it's important to understand, again, the function of those filters so we know how and what kind of role longevity ends up being played in these types of systems. The other aspect of this filtration we need to discuss is this sorptive media filtration. So this is where we have a reactive media that can target specific types of pollutant. What are some examples? Biochar, zeolite, compost, right? So these work in parallel with the physical filtration and sedimentation that we see in the inert media, but that reactive component allows you to target the pollutant that, say, would be bound to the media. So this allows us to target the dissolved fraction of the pollutants we're trying to reduce, and often can act as a polishing filter at the end of a treatment train to grab sort of that other half of the pollutant. So we've got the particulate taken care of from a physical side and physical filtration side of things, and we can often do sorptive media to it can act as a standalone, but can also then boost that overall performance. An example of that would be context phosphosorb media. It allows us to target the dissolved phosphorus fraction. So what is the other dominant process at play in this category? And when we're thinking in the pond sense, that dominant process ends up being sedimentation. So again, this is something that's reliant on gravity and time. That's why if we want more contact time for the volume of runoff we're containing to be in a pond, our pond gets bigger. And this is characterized by Stokes' law. How does a sphere fall out of the water column, essentially. All right, and that's really all based on, how quickly the particles will settle. And again, that's going to be based on the size of particle that we have in the system, right? And so what are some factors that then affect the ability for SCMs in this category to filter and settle? The contributing drainage area can be a factor. So we don't want to overload our filters. And so there is a general rule of thumb of about 5 acres for filters. We can do more drainage area for ponds. Ponds get bigger the larger drainage area we serve. Both of these then have distinct surface area needs. From a filtering standpoint, that surface area, while large overall, it comes in a compact form. Whereas with a pond, we need a larger surface area for it. And generally that means more land needs. The type of media we're selecting has a pretty significant effect on how effective those filtering practices are going to be. We need to make sure we can maintain these systems. Again, all SCMs are going to need maintenance. All filters include, all ponds eventually fill up. We need to be able to assess or access these systems. We also want to think about how can we extend the life cycle of these types of practices. And so we have pretreatment needs associated with both of these practices that can help with that. In this example, the new rules actually say a pond forebay must be 10% of the water quality volume. And so we're going to see manufactured proprietary systems. We're going to see ponds with forebays as part of this category. Lastly, under the category, we're going to be looking at hydrodynamic separators. So this is going to be in category 4. We're going to treat the max runoff generated from the 1-year storm. This is not all manufactured systems. Again, this is a very specific type of the manufactured suite of products. HDS really work similarly, actually, to ponds, and that's where the origins of HDS come from, and that we see swirl concentration and gravity separation, as well as some flow controls to minimize resuspension, turbulence in the system, slow down the runoff because these systems work better. The slower runoff goes, it allows more time for sediment to fall out. And so, again, what is the dominant process? So just like what we saw with the last category and ponds, sedimentation plays a distinct role. On the right's a really cool computational fluid dynamic illustration here of one of our systems, and you can really see where we expect the sediment to fall out in this device. And again, it's characterized by contact time in the system. And what are some of the factors that affect HDS performance? So one, we want to make sure that these are tied to an appropriate flow rate. We want to make sure we're not undersizing these systems. All of that should be tied to some kind of performance testing, and the rule reflects the need for an industry-wide standard to be used. Sediment particle size affects HDS performance. So these are systems that are really good at large sediment removal. They're going to be less efficient at finer sediment. Residence time, as I discussed, becomes a pretty critical factor in all of this. The longer you can make a flow path, or the more time the sediment has in the system, the more sediment can actually fall out. We also want to mention that we don't want to, in these types of systems, we want to make sure that they have passed some kind of a scour test so that we then don't resuspend and potentially lose some of that captured sediment. So because this particular treatment category is fairly limited to hydrodynamic separator systems and similar proprietary practices, that's what we can expect to find in use as part of the treatment toolbox. And depicted here are 2 examples of specific hydrodynamic separators offered by Contech. This is not meant to be an all-inclusive category related to manufactured systems. This is very specific to hydrodynamic separators. As we talked about throughout this presentation, proprietary biofilters and proprietary filters fit into other parts of the toolbox and are not subject to the requirements found in this particular category. Another key piece of this category is that if you are utilizing an industry-wide standard as required by rule, and TDEC has defined an industry-wide standard as either the program from Washington State, which is the Technology Assessment Protocol Ecology, or the certification program from New Jersey, which is the New Jersey Department of Environmental Protection's certification. Those have a ceiling of 50% for these types of practices. That would keep them below the minimum 80% requirement and therefore not be allowed to use as standalone systems. Another key distinction to point out here is that NJCAT, which is the New Jersey Corporation for Advanced Technology, it's a public-private partnership that verifies performance of these types of systems, has no regulatory authority in the state of New Jersey, and it is not equivalent to NJDEP's certification program. We also want to talk about treatment train guidance here. I think it's important. This is particularly important as we talk about how we're going to use hydrodynamics separators moving forward. This is that fourth category. Again, by rule, we have a sort of a minimum of 80% TSS that we're trying to achieve. That is not the rule, but that's kind of the target. And this treatment train using HDS describes how you can achieve that. The key consideration within this is that distinct unit removal processes are needed to create effective treatment trains. That means that two of the same HDS systems in sequence are not going to create additional performance for your system. Good engineering practice should prevent two HDS systems from being lined up to try to achieve this treatment train equation or result for 80% TSS. In fact, if you went so far as to try that, you would actually need 3 HDS systems. But again, that's not the intent of the rule, as well as it's not sound engineering practice to use that type of system. We need distinct unit removal processes to create effective treatment trains.
Now that Jacob's laid an excellent foundation for us in understanding all of the key parts of the new water quality treatment table and all the different SCM treatment types, I'm going to take that one step further, and we're going to go through the important considerations when designing for treatment with proprietary practices in mind. As previously shown in this presentation, Contech has a vast portfolio of solutions that can meet each of these SCM treatment type categories. Therefore, I'm not going to go through the intricacies of each design because I can get very site specific. Instead, I'm going to take broad strokes and discuss how we might calculate things like the water quality treatment volume or convert that to a flow rate that then can inform our design procedures for each of the types of practices we may be selecting to meet this table. To meet those requirements, I kind of see us as needing 3 components. And those 3 components are the first being water quality design storm. That's very clearly defined here at the top of the table as the 1-year, 24-hour storm according to NOAA Atlas 14 data sets. Building off of that, we have the water quality treatment volume, and this is how much volume we need to ensure that we're capturing by our SCM for treatment to ensure that we're meeting the treatment goals outlined by this new permit. And so that volume is defined as the runoff generated from a portion of the design storm, depending on what practice you've selected. And also the runoff that is generated from the impervious surfaces is really all we're considering here relative to the water quality volume. So we're going to keep that in mind as we're doing our design calculations in the rest of these slides. Finally, the third component, and perhaps the biggest component, is making sure that we're designing stormwater control measures to achieve a full treatment efficiency of at least 80% TSS removal from that volume. Therefore, that means if you're using a treatment train, the sum of that treatment train calculation needs to equal at least 80%. So when we are defining our water quality treatment design storm, I find the quickest and easiest way is to visit NOAA's website for precipitation frequency data server using the NOAA Atlas 14 data. And from there, I'll select the state. In this case, we'll select Tennessee. And then we're faced with a screen very similar to the one I've got shown here. And the first option we have, or we're presented with on this page, is to either select precipitation depth or precipitation intensity as far as the data type that it's going to produce for us. Which one you select here is dependent on what type of design method you're planning to use for defining the hydrology of your site. So if you're going to use the hydrograph method like TR20 or something similar, you're going to need a precipitation depth. If you're going to be using the rational method calculation, you need to select precipitation intensity. So pretty straightforward. From there, you can also further dive down into a more local area or rainfall station. In this case, I'm just going to be using Cookeville, Tennessee to generate my numbers as an example. So let's look at precipitation depth, the hydrograph method first, like TR20. So I've selected precipitation depth, I've selected Cookeville, and I'm going to be presented with a table very much like this one. We have two components that we need to look for to pull our value off the table. We need duration, that's the duration of the design storm, so we know that's 24 hours. And I also need the recurrence interval of the design storm, that's 1 year. So that shows us that we're looking at 3.05 inches as our design storm depth to create the hydrograph that we're going to be using in our calculations. If we're going to be using the rational method, we then can look at precipitation intensity instead. The key difference here is the duration that we're selecting is not the duration of the design storm, rather it's the duration of the time of concentration for the specific watershed in question. So for sake of example, if we have a 10-minute time of concentration on this project, we'll select 10 minutes instead of 24 hours. Our recurrence interval still is 1 year, and that shows us that we are going to be using 3.65 inches per hour as our design storm intensity in the rational method equation. This is important to know that the duration is based on time of concentration and not the duration of the design storm, because if you're going to use the duration of the design storm at 24 hours, you're going to be using an intensity far lower than we actually need to be treating, and you're not going to provide the required amount of treatment at all. So it's really important to get that part right if you're using the rational method. The second component, calculating the water quality treatment volume. I think this is also pretty straightforward. I like to use the SCS runoff curve number method as I've outlined here on the right side of the screen. It's really easy. We really only need two variables, sorry. We're going to be calculating Q, the runoff, in inches. We need to supply variable P, that's rainfall, precipitation in inches, and also the potential maximum retention after runoff begins, S. Because we're looking at the runoff generated from impervious surfaces only, the curve number then we can set to 98, and that means our S value will always be 0.2 inches. So very easy. And then precipitation is variable based on whatever SCM treatment type we select. So if we're using a row 1 infiltration type base, we're going to be selecting a P of 1. For row 2 would be 1.25. For row 3, we have the option to either select the first 75% of the design storm depth or 2.5 inches, whichever is lesser. So we know our full design storm depth is 3.05 inches from previous slides. 75% of that is 2.29 inches, which is less than 2.5. So we're going to be using 2.29 inches as our precipitation depth for this row 3 practice in Cookeville. And then obviously for our row 4, 3.05 inches. So then we can take those P and S values, calculate our runoff in Q, and we'll take that runoff depth, multiply it by our watershed area. So for example, a 1 acre site, 1 acre multiplied by your runoff depth is going to give you a water quality treatment volume. You just need to make sure you're converting your factors appropriately. I'm going to use factors appropriate to result in cubic feet. If you're looking at the differences between row 1 and row 4, you'll see they're quite significant. Those infiltration row 1 type practices are looking at just under 3,000 cubic feet of volume to capture, provide treatment for, whereas row 4, we need to capture the full 10,200 some odd cubic feet. So quite a difference, and that's really important to consider the differences when you're selecting your stormwater control measure type for the practice, because it does inform how much volume you need to make sure you're capturing and treating on site. Not all SCMs are designed on a volume basis for volume capture. Sometimes they're designed based on how much flow rate you're passing through them. We call those flow-based practices. And in those cases, we need to convert the water quality treatment volume to an equivalent flow rate. And doing so really requires us to use one of two methods, whether we're using a hydrograph method or the rational method. Now, personally, I recommend the use of a hydrograph for all 4 SCM types, but if you would like to use the rational method to calculate your maximum peak runoff, the rational method is mostly applicable to row 3 and row 4 practices for reasons which I'll explain in the next couple slides. Um, but personally, I do prefer to use a TR20 hydrograph method for all of them because I find it makes it most simple for my calculations. But you can be the judge of that on your own projects. Um, so in order to convert that water quality treatment volume to a flow rate, we do need to create a hydrograph, at least for this first method. I'm going to go through the hydrograph method first because I find it mostly applicable. In order to create this hydrograph, we need a rainfall distribution because we need to know how the rain falls in the project's geography, since rainfall is quite temporal. Historically, we used to use the NRCS Type 2 method in Tennessee, but that's actually not compatible with NOAA Atlas 14 rainfall data. It's quite conservative. So we should be using these newer Ohio Valley distribution that I have shown here, that I grabbed a snippet from the National Engineering Handbook. And this just shows us we've got the NOAA A, B, C, and D distributions. In Tennessee, we're only seeing A, B, and C popped up on this map, so I've just included a graph of rainfall depth versus time for each of those 3 here. For Cookeville, we're in the blue zone, so that's going to be NOAA B distribution that we'll use to create our hydrograph. So we have all these site inputs, and we'll just plug them into whatever software we're using. In this case, I'm using HydroCAD. You can use whatever TR20 software you might be interested in using, but for me, that's just what these printouts are going to be. They're HydroCAD printouts. So we have our site characteristics of 1 acre, curve number 98, time and concentration 10 minutes, all this stuff we've talked about before. Rainfall characteristics, we're using a NOAA B rainfall distribution, and a full precipitation depth for the design storm of 3.05 inches. You might be tempted here to put in either 1 inch, 1.25 inches, or 2.29 inches as your rainfall depth, but that would be incorrect. We need to create the full design storm hydrograph in order to calculate the equivalent flow rates for the top 3 row practices. And I'll show you why in the next couple of slides. But the language is very specific in the water quality treatment volume table. It says the runoff generated from the first 1 inch of rainfall. So that means we need to generate the full design storm curve and then partition out the flow rates equivalent to the target volume. So we put all these site inputs into, say, HydroCAD, and I would get this sort of printout. So for this project example, my peak runoff is 3.10 CFS for the maximum, 1 year, 24-hour design storm. That peak runoff is what we would target for a row 4 type practice. You can also see here, I've got some additional information that confirms my previous calculations for water quality treatment volume. For example, total volume being 235 acre feet. That's just a little over 10,200 cubic feet, which does match our previous SCS curve number runoff method calculation. All right, so we've generated this design storm hydrograph. We need to then find out where on this curve does the first 1 inch, first 1.25 inch, and first 2.29 inches of rainfall occur. So the way I do that is I will then look at the runoff depths because I can get the printout of this hydrograph in for runoff or corresponding to runoff depth, and those runoff depths will then correspond to a runoff rate. So, for example, a runoff depth of 0.79 inches for that first 1 inch of rainfall corresponds to a runoff rate of 0.63 cubic feet per second on the rising limb. The area under the curve to the left of the right vertical red line, that area under the curve corresponding to 0.63 CFS does actually match the water quality treatment volume we calculated before. For row 2, a 1.25 inch precipitation corresponds to 1.04 inches of runoff depth, which then corresponds to 1.06 CFS on the rising limb runoff rate. So those are the two flow rates that we would target if we were designing a row 1 or row 2 practice on a flow rate basis, because those flow rates correspond to an equivalent water quality treatment volume. However, when we look at row 3, we see that row 3 runoff depth corresponds to 0.52 CFS, which is on the falling limb of the hydrograph. So 0.52 actually occurs in two spots on this hydrograph, one on the rising, one on the falling. Because our runoff depth actually occurs after the peak flow rate, if we were to target 0.52 CFS, divert only 0.52 CFS to treatment, and then divert the remaining away from the treatment, we would not be capturing the full water quality volume. We would actually be capturing less volume than we would in a row 1 practice. So in order to ensure that we're capturing the full water quality volume, row 3 practices should not be targeting their specific runoff rate that corresponds with the depth. Should actually be targeting the maximum peak runoff, because that is how we ensure we capture the full water quality treatment volume. So this will actually happen for all row 3 practices in Tennessee. The rainfall distributions for NOAA A, B, and C all find the first 75% of the design storm, or 2.5 inches, occurring after the peak of the hydrograph. So for row 3 and row 4 practices, we should be targeting the maximum peak runoff flow rate for a flow-based design. What this means is we can use the rational method for row 3 and row 4, because we can't partition the flow rates for the rational method like we do for the hydrograph method. So in this case, we have runoff generated from impervious surfaces, resulting in a C value of 0.95. We know our intensity from previous slides as being 3.65 inches per hour, and also our acreage of 1 acre. All that multiplied together shows that our maximum peak flow rate based on the rational calculation method would be 3.47 CFS, just a little bit over 3.10 that we generated from the hydrograph. And all that those are the kind of key components to wrapping up your SCM design. Once you know your volume you're targeting and your flow rate, you can then select an appropriate stormwater control measure that is designed to meet those inputs, and then from there, build into the rest of your site design hydraulics, etc. One key component of the policy, the new permit, is that maintenance of SCMs is definitely required. The rules state that SCMs must be designed to provide full treatment capacity within 72 hours following the end of the rain event for the life of the project. If we don't maintain our SCMs, proprietary or non-proprietary, eventually their performance is reduced. If the performance is reduced, we're no longer meeting the rule requirement to provide full treatment capacity. So maintenance is important and must be done for all SCMs. So we would encourage NPDES to develop and implement SCM maintenance procedures, as part of their rule implementation. But also, it's important to consider maintenance at the time of design. Because if you're considering your maintenance access, if you're considering maintenance frequency, maintenance cost, the tools you might need, all these things are really helpful in choosing the appropriate stormwater control measure for your site. Because if you can't access it to maintain it, it's probably not a good solution. So we really should be thinking about maintenance at the time of design. We have on our website a lot of maintenance guides that can be used to inform those decisions. Also, I think that legally binding maintenance agreements could be appropriate wherever it's applicable to ensure that owners who are taking ownership of a site will continuously provide the maintenance that is required to ensure that our water stays clean. Another key component of maintenance is inspection. Not all failure modes result in visible problems. So it's really important that we inspect our SCMs more often than we maintain them, because continual inspection, say quarterly or biannually, would help you know how often you need to be maintaining the SCMs, on any given site. So this is really important to consider maintenance and inspection at the time of design, and especially since it's a required part of this new rule. If you're interested in more information about context treatment solutions, I encourage you to visit our website, www.contactes.com. On our website, you'll find helpful links for project assistance, like our Contact Design Center and product design worksheets. If you're looking for more technical information, like detail cut sheets, approval letters, maintenance guides, and other product literature, those can be found on each of the respective product pages as well. We also have PDH articles, case studies, product videos, and blog posts for those of you who are interested in expanding your knowledge of our solutions. And we also have a list of certified maintenance providers, which are third-party companies that are trained to maintain Contact products, and they can help you with scheduling or quoting maintenance for installed systems. And that concludes our presentation today on tools for treatment, the science behind treatment strategies for new NPDES Rules Compliance in Tennessee. Thank you for your interest in this topic and for your attention for our presentation. If you do have any questions on the material we've presented today, please feel free to reach out to Jacob or myself with those questions, and we'll be more than happy to answer them. So, thank you.